Hey guys, welcome to this YouTube short. So in this short, I wanted to discuss an interesting idea, interesting concept. You may have heard of self-avoiding random walk. It's a very interesting concept. So basically, if you in a self-avoiding random walk, you can just Google it and check the animations, GIFs, or just the concept in general. Suppose you have a curve. This is also we see this in chaos theory, space filling curves or piano curves. So these curves, if you just simulate the system, they will try to cover all the points, the entire space. Suppose you have a one-dimensional line and it will try to cover the entire two-dimensional space without intersecting. So it will avoid its own path. That's why it's called self-avoiding. Like it will never come back. It will try to cover all the unique points, in the curve. It will try to cover the entire space. And this behavior is seen, for instance, when a river flows. The river does not come back and intersect itself. The river flows in one direction. If it meets with some obstacle, maybe some rock or something, it can bifurcate, or it can just curve, just divert its flow. But a river never just comes back and forms a loop. Why? Because you can think of it in two ways. This is actually, you can try to think of this from the perspective of statistical mechanics. There is something called postulate of equal a priori probabilities in statistical mechanics. It says that all the microstates are equally likely. All the accessible microstates of a system are equally likely. So if you think of this space as the phase space, then each point on the phase space is actually a microstate. And so since all the microstates are equally likely, then the phase trajectory will try to cover all the allowed microstates, all the accessible microstates, without it will not try to intersect or come back to the same microstate twice without having covered the other possibilities. This actually holds for systems that respect ergodicity, the ergodic hypothesis. Because see, if a system does not cover all the possible microstates and comes back to one of its previous states, that means intersects, then that doesn't really fit in with the postulate of equal a priori probabilities. Now you can also think about this physically. You may think that because if I just exclude the possibility of the system intersecting its past path, I am leaving out some configuration, so the entropy is decreasing. No, it's not that. It's also true that if the river intersects itself, or if the path intersects itself, then the energy or something that is not really uniformly distributed, right? If there are intersections, for one, if a loop forms, the behavior becomes predictable, periodic, and that doesn't mean entropy is increasing. That is like the system is becoming predictable. For another, if you think about it like in terms of energy, like for a hypothetical system, then intersecting means the energy density is increasing at that point, so it's not really uniformly distributed, and that doesn't mean an equilibrium system. But everything, as we know, tends towards equilibrium. Just some rough ideas, insights I wanted to share about this. I hope you find this interesting and insightful. Comments are welcome, of course. Yeah, thank you.